No holidays, no? So which chapter have we studied in your school? Light and?
Light and
We will just study.
Sorry. Dhoni. But another way.
You see the ICC results?
Yes, my mother's.
Yeah. It's 499 out of 500. Yours is also best of 5 only, no? CBSE is also best of 5. ICS, all India ranker is 499, and there's one child from UT class taking.
Ma'am, but it showed 500 out of 500.
It's yours, all India ranker.
St. Mary's.
St. Mary's is 499.
Mine was 500.
So what they've said is all India rank number 1. There are 3 of them, I think, that left you. Want to have the fan on for some time? You will switch on the fan for some time, afterwards you will switch it off. Fan. Keep the last fan on for some time. 5 minutes afterwards we switch it off. Keep the hot on again. I think CBSE results will be out next week. Any time now, that's what they're saying. Any time now. Somebody is saying tomorrow.
it was supposed to be today, but it so they're officially
Yeah. Usually it's out of. So actually they were saying out of usually it was in May, mid-May, but now for most of the boards they have competition. This time CBSE is having 4 sets of exams now. 2 exams right now. So don't even look at it. Do the first one properly and then read it. Don't even think of the second exam. You want to get finish it off. Otherwise again, you must not be one. Sure, no. Shall we start? Ready with your books and all? So what is the last thing that we were doing? Resistivity, yeah, last time. Let's just revise whatever we have done last time. Resistivity and resistance. Okay, we'll start with that. So if we just recall what is meant by resistance and resistivity. Okay, Ayush, what is resistance and what is resistivity? I want you to recall because we are going to build up on this things. What's happening? What do we mean that the wire has got more resistance? So what happens to the current?
Stops the current.
Okay, not necessarily it stops. Reduces the flow of current, you can say. Okay, then what else? How do we measure resistance? What is the unit? Ohm. Okay. And what is the formula? How can you find out R? Okay. So therefore, you can definitely use Ohm's law and find out V by I is equal to R. Okay. R is a constant, right? R is a constant and it also depends on this one, V and I. What happens if V is increasing? What is V? What is V stand for? Potential. What happens if potential difference is increasing? Talk in terms of current. What happens to current? If potential is greater, increases. Greater the potential difference, the greater is the flow of current. Think always in terms of waterfall. The greater the difference between the two levels, obviously greater is the waterfall. So think of the same here. So greater V, greater is I. Will R also become greater? If I'm increasing. Why do we say R is a constant? For a given value of V, if V is increasing, I is also increasing, no? So the value of R is going to be a constant. Did I give you the table yesterday? What is the table graph, all that you see? What happens to the last column? R is equal to a constant, no? Values, look at the values. So what is happening? V is increasing, I is also increasing, but the value of R remains a constant. Yes, that graph, you see that graph and the table is on that. Yeah. So what did we write? On the y-axis, what have we taken? We have taken y-axis, we have taken voltage, and on the x-axis, we have taken I, which is the current. So as voltage is increasing, what is happening to I? I is also increasing. Therefore, R remains a constant. You understand? Okay. Now we talk about rho. What is rho? Resistivity. Okay. And what is the unit for resistivity? Ohm meter. Okay. So we have seen that SI unit is ohm meter. So what is the formula? R is equal to?
Rho L by A.
Correct. So R is equal to rho L upon A. Okay. R is the resistance. Rho is the resistivity. L is the length of the wire. And A is the cross-sectional area. Use the word cross-sectional area. Imagine that you have cut the wire and that is your cross-sectional area. Therefore, if I have to rearrange this and talk in terms of rho, what will I say? Come on. If you cross multiply, what will you get? R A upon N. Okay. So, resistivity you can find out in terms of ohm meter. If I know resistance, area of cross section, and length. Okay. But I told you last time that area will not be given to you. What is area? What is a cross sectional area when you cut a wire? What is the formula for area? Come on, tell me. Pi R square. Yes, so pi R square is given. Okay. Sometimes R is not given. And what if D is given? D is nothing but the diameter. So D by 2. Yes. R is nothing but D by 2. Whole square pi is nothing but your area. Is that okay? So in yesterday's last time we have done the sum. You remember that there was a 4. How did you get a 4? It's obviously because it is 2. Okay, in the denominator, square, that is 4. Is that okay? So if you do this, you will have to substitute. So here you will get ohm, you will get R, which is resistor. Area, this is what you have to substitute for area there. So you will get it as pi D by 2 whole square divided by what you have here is length. Is that okay? So all that you have to do is to substitute the value. Is that okay? Now, when you look at the table there, we were talking about resistivity. The table which is given in your textbooks. This table. Resistivity of some of the metals. Okay. Alloys. Did you see that? This is on page number 179. Conductors. If it is a very good conductor, you see some value times 10 raised to the power of -8 ohm meter. Okay, so this is the value of resistivity if you look at the table. You see the value, it is so low. So if the value is very low, that means it's a very good conductor. Okay. Second, somewhere in the middle, we are also talking about alloys. Alloys will also have some number, but you see that it is 10 raised to the power of -6, something raised to the power of -6. Once again, it is an ohm meter. That means alloys are allowing the current to pass through, but it has a good amount of resistance. So such type of wires are the ones which are used for, let us say, bread toaster or for heating purposes, okay, where you actually require some kind of a resistance. Further down, we are also talking about an insulator. What does an insulator do? Does it allow the current to pass through? No, it's a very bad conductor. Now, if you look at the values there, how much is it? What is the value? Something 10 raised to the power of how much? Yeah, they've given you 14, 13, 16, okay. So that means it is very high. So if the resistivity is very high, it becomes an insulator, right? So there's no need for you to learn these numbers, but you must know which is a very good conductor. Which one is the first one there? Which one is it?
Glass.
No, very good conductor I'm saying.
Silver.
Something that conducts electricity. So obviously it's silver. Okay. An insulator, you can talk about wood or glass or paper or whatever it is, because it can conduct electricity. So we have done all this, right? This page we have completed. We have also seen examples 11.3, 4, 11.6. Also, yeah, 11.6. We will do it later. Yeah. Come on, let's look at the questions, in-text questions before we start off. First one, I'm on page number 181. And then here you'll have to leave out a couple of pages. I think you missed 2 periods, I think, 2 classes. Question. First one. What's the answer there? On what factors does the resistance of the conductor depend? Here. In-text question. Here. Come on. First question. Why don't you get your textbook, because you know that you'll be following the textbooks. Okay. What are the factors that the resistance depends upon? Now let us look at this formula. Look at the board here. Your resistance is depending upon what? On length and cross-sectional area. Okay. So if the length is more, what happens to R? R is directly proportional to length. And R, you can make out that it is inversely proportional to area. So as the area is increasing, resistance is decreasing. Okay. Here what is happening? As the length is increasing, the resistance is also increasing. So there's another factor. We are also talking in terms of not only length, not only the area, but also about the temperature. Okay. As the temperature increases, the resistance also increases. Take down this quickly, come on. First one. Don't write the question, just write down the answer. Okay. The factors are, we are talking about the factors of resistance. The factors are what? Length, cross-sectional area, and the third one is temperature. That is resistivity. Length, cross-sectional area, temperature. upon the material resistance. It does. Why did we call about it good resistance, bad resistance? Okay, good conductor. We talked about insulator. That is also there. Okay, when we talk about the resistivity, it depends only upon that, nothing else. Okay, so you can also write down. It also depends upon the material, whether it is silver or paper or wood or whatever it is. Look at that second question. Arush, what is the second question and what's your answer? Will current flow more easily through a thick wire or a thin wire of the same material when connected to the same source? It will flow more in thin wire. You feel that? Why do you think it is a thick wire?
Because the flow current will be more.
Yes.
The current will be less.
No.
The resistance will be less.
Thick wire. Suppose I take a thick wire like this, as when compared to let me have a pencil or something like that. Yeah. Let's see now what is happening. Look at the cross-sectional area. Cross-sectional area for a thick wire is more. So the flow of current is definitely more. Okay, because resistance is less. Here what is happening? Cross-sectional area is less, therefore resistance is more, and therefore the flow of current is less. So what we have to do is this. All of you look at the formula here. You have to explain with reference to the formula. Resistance is inversely proportional to cross-sectional area. As the cross-sectional area increases, the resistance decreases, and therefore the flow of current is more. Come on, hurry up, write it down. Okay, first write down the formula. R is equal to rho L upon A. If the cross-sectional area is more, you write a full formula, and with respect to this, we are going to talk about. If the area is more, resistance is less. As in the case of a thick wire. Correct. Okay, now you talk about a thin wire. In a thin wire, what is happening? Yes, it is smaller. Cross-sectional area is smaller. Therefore, R is more, and therefore the flow of current is less. What did you write? Rashita, what did you write? Is that statement correct? What did you write? If the area, if the cross-sectional area is small, then the resistance is high, and therefore the current will be less. Okay. Karam, next section, next question. Let the resistance of a third one.
Yes, sir. Let the resistance of an electric component remains constant, while the potential difference across the two ends of the component decreases to half of its former value. What change will occur in the current through it?
So what all are we talking about? What are the three things that they are mentioned there? Let the resistance remain constant. Okay, so R, they have said that it is going to be a constant. And the potential difference between the two ends is reduced to half. Okay, now they are talking what change will occur in the current. What is I? I is equal to current. Did you notice what are the three things that we are talking about? Which formula can we refer to? Ohm's law. What is the formula there? V is equal to I into R. Okay. So they are asking you what is happening to I, which is current. So if V is decreasing, what will happen to I? That proves it is directly proportional, no beta. V is directly proportional to I. So what is happening? V is decreasing, therefore I will also decrease. Because R is a constant, isn't it? Come on, write down. According to Ohm's law, V is equal to IR. Okay. This shows that V is directly proportional to I. First is Ohm's law. Second point I said, it shows that V is directly proportional to I. If V is decreasing by half, I will also decrease by half. Yoshita, you can write it in your own words.
What we have to write that.
I'm putting it up on the board. Okay, look here, I put up all the points on the board. It's not necessary that you write exactly as what I'm saying, okay? But these points should be there.
Last point would be V.
If V is half, I will also become half. Okay, because R is a constant and that is given to us. Okay, Anish, fourth question.
Wire coils of electric crystals and electric ions made of an alloy rather than a pure material.
Okay, now we are talking about two things. What are the two things that they are asking? One is a pure metal and the other one is an alloy. What is an alloy?
It's just two or more metals or non-metals.
Not necessarily. We can, yes, we can also write down an alloy is a homogeneous metal of two or more metals or even a non-homogeneous. But why do we use an alloy? When do we use? What is the other thing that they are given? For what type of appliances? Electric toaster. Toaster में क्या होता है? When you switch it on, it becomes red hot. So what should be the property of an alloy? Resistance should be comparatively high. Yes, it should not be melt. Otherwise, the whole thing will melt. No? So it should have a high melting point. It should not melt, and it should have a reasonable amount of resistance so that the coils become hot. Will you be able to write that? First point, define what is an alloy. Come on, write down. An alloy is a homogeneous mixture of two or more metals. And maybe you can give an example like nichrome or something of that sort. Example, nichrome. Okay. Nichrome is an alloy of what? Steel we usually don't use. Though it is an alloy, but not for such purposes. Okay. Nichrome is an alloy of what? Nickel, chromium, manganese and iron. Okay. Second point you will write. An alloy has a high melting point such that it does not melt. Third point you will also write. Okay. Also, resistivity is what? Now I am referring to the table there. Resistivity is higher than that of a pure metal. Okay, come on, write down. Resistivity is higher as when compared to the pure metal. Okay. The last question then. Yes, maybe last one. Question number 5. Use the data. Refer to the data. Iron and mercury. Same table. We were referring to the table. No? They have given you. Which one is a better conductor?
Iron.
Why is iron better?
Because the resistivity is high.
Resistivity is higher means it is a good conductor or a bad conductor?
It's a good conductor.
See, iron is how much? 10 into minus 8. Okay, and look at mercury. It is 94. So 94 is, and that is also 10 raised to the power of 9 minus 8. So which is a good conductor? Iron is a good conductor. Come on, right now. The thing is, you'll have to look at that indices, huh? Don't mistake that. It has to be the same index.
Learn this.
I told you many times, you don't have to learn the values, but just know in which order it's. Okay, next one. Which material is the best conductor? Silver. Now I want you to refer to some questions which are given in the last page of the lesson. Question number 7. Please refer to question number 7 because it's with reference to Ohm's law. Okay, let's read the question. The values of current I flowing in a given resistor for the corresponding values of potential difference is given. So value of I is given, B is given. Will you see that? I is 0.5, B is 1.6. I is 1. What is happening to B? B is also increasing. So did you see that? We are talking about Ohm's law. Now what? Lot of it. What's happening here? What's happening? 7. Question number 7. Forget it. Forget it. If people don't have Facebook, that is what happens. You keep on hunting for it and disturbing everybody around. Just leave that Ohm's law. That's it. Okay. Then plot a graph between B and I and calculate the resistance of that resistor. How will you do? I've given you already one table. Okay. Now this is for your homework. Right? This is for your homework. So how will you draw it? I will tell you now, and afterwards you can plot it later. Come on, take it out. Value of I, corresponding value of B, and calculate your value of R. First, second, third, etc., etc. Value of I is 0.5, 0.5. This is in amperes. Okay. Second one is that okay? So you're going to take down the values, right? Is that okay? How will you calculate R? Ohm's law, correct. So this is equal to V upon I. You know V, you know I. All this will be a constant. More or less, you can predict this a constant because that's what we have seen. Now he's asking you in the book. They're asking you to plot a graph. So you're going to take a graph paper like this. Use this, and you're going to plot it on the same way. Y-axis will contain B, X-axis will contain I. Look at those values, and you're going to get a graph something like this. Okay? And what did we say? Delta V upon delta I will give you the value of R. Is that okay? R is equal to V upon I. I've also worked it out. Just some examples I've given you. Delta V and delta I. So any two values of V you take, see the corresponding value of I. This is your delta I. This is your delta V. And this divided by this will give you the value of R. Will it be different or the same value of R? Different. Will it be different? What do you think? Will it keep on increasing because I is also increasing? What did I say right now?
No, it would be same.
It is a constant. R is a constant. It will not increase. It's a ratio of V and I. V is increasing, I is also increasing, isn't it? Isn't it? So this value of R will remain a constant. Did you understand? So here, this value of R, you will get a constant. See, V upon I, how much is it? Right now you can make out. How much is it? Approximately everything will come out to be the
For
same.
the first one, it's 3.2.
Slightly, maybe. It is an experimental value. Some student has worked on it. But for most of the values, it will be the same. Understood? Put a tick mark, homework, and leave at least half a page for your calculation and teaching because I will check it out. Yeah, I was present. It's 2 minutes. That's correct. Approximately, you get the same. Not 33. Whatever it is, 3.4 right here. V upon I. 3. See, 2.0 are divided by 6.7. 6.7 divided by 2 is 3 point. Decimal wrong here. Sorry. Okay. Now look at the next question. See the, is it okay? Just check it out. Okay. Let's come to the next section. Next question. Question number 8. Okay. What is given to us and what should we find out?
Potential difference.
This is your question number 8 we are doing. Okay. When a 12 volt battery, what is that 12 volt? That's your potential difference or your voltage. You can also write it as potential difference. Okay. Unknown resistor. Then there's a current of 2.5.
We have to convert it.
What is that small n? Milli. Yes.
Milliamp.
Milliamp. So you have to convert it into amperes. So current is given. What alphabet should you use? I. Remember that it is I because it's in amperes. Okay. So immediately you have to convert it into amperes. How will you do it? Milliamperes to amperes. How will you do? Divide, multiply. What will you do? Milli
divided by I.
Milli is 1000. Okay, so you're going to divide this by 1000. So that will give you your answer in amperes. Then to find is what? Find the resistance. Find the resistance of the cell. Which formula will you use? Yes. Ohm's law. Okay, so your formula here is R is equal to V upon I. So V is 12. I is how much? 2.5 upon 1000. So this will go on the top.
How much 4.8?
Which one?
This one. Answer.
Answer. 4.8 what?
But at the back it's given KO.
What is the K? It's low. You got the this thing, attendance sheets. Okay. Okay, boys, here. How will you do this? Okay. It is 2.5 divided by 1000. So you can also write it as 12 divided by 2.5 into 10 raised to power of 3. This is on the top. So this value you find out. How much is it? Find out this value. Times 10 raised to power of 3. 10 raised to power of 3 is nothing but kilo. That is why they are talking in terms of kilowatt. Kilo. R, no? It's R. Oh. See, boys, I don't like it to be constantly checked. And I cannot keep on telling you. But the next time I find anybody talk now, I'll be putting you all in different corners. I'm sorry to tell you. Did you understand what I've done? Yeah. How much is that? Did you get it? Did you get this as how much?
428.
Yes. So your R will be in O. Okay, but because of this 1000 here, you can also write it as. So put a tick mark for 7, 8, and the rest of it is all different. Power is there, etc. Okay, look at question number 5, which we have already completed. See question 5. How is a voltmeter connected in a circuit to measure the potential difference between 2 points? Voltmeter, is it connected in series or is it connected in parallel? First time, my first class itself, I showed you.
Voltmeter is connected in series or
Parallel.
and
Ammeter is in series. Okay, so make a note of it. Voltmeter is always connected in parallel. Okay, now let's come back again to page 181. All this time we were talking about a circuit which is closed. Okay, and we know that if at all there is a circuit which is open, there's going to be no flow of current. Let's talk about a simple circuit diagram, which is something like this, as simple as it can be. So what is this one? You can have a nichrome wire, you can have a bulb, you can have a torch bulb or whatever it is. This is providing you the resistance. And this, the bigger line is the positive terminal and the smaller line is the negative terminal. The current is flowing from positive to negative. So always it's necessary for us to show. How do we measure the amount of current which is flowing? What should we have? Ammeter. So where are we going to put the ammeter? It is in series. Okay, so you can put it on the wire itself like this. So this is your ammeter, which is going to measure. But now we are also talking about a voltmeter. How is a voltmeter connected? It is connected in parallel. So always you're going to have a voltmeter which is connected in parallel to the resistor. Because I want to find out what is the potential difference between these 2 points. It can be between points X and Y. Is that okay? Suppose I want to increase the current. What will I do? Instead of having one cell, I can have another one. Okay, so then we have a battery of cells. So I can have another one, maybe I can have another one. Did you understand the diagram? Okay, on page number 181. And now I have just about started with one resistor. Did you notice that there is only one resistor? So I'll talk about R1. Let's say instead of having only one resistor, I want to have a couple of resistors which are in series. So I'll have R1, R2 and R3. Now these are resistors in series. Because they are in series, I'm going to write it as RS, which is showing that it is connected in series. What did we notice here? Immediately we can notice a couple of things. That it is the same current which is passing. Did you notice? Just like a pipeline. There's only one pipeline, so the same amount of current is flowing through. Okay. Now I want to find out what is the total resistance of this. Whether it is going to be increased, whether it is going to be decreased, etc. etc. Okay. So how can we find out? For each time, I'm going to have a voltmeter here. Suppose I have a voltmeter and it is giving me a measurement V1, which is corresponding to R1. Is that okay? Then I'm going to discontinue. I'm going to put it across R2 and the value will be V2. Similarly, I'm going to put it across R3. I'll get these three experimental values. It can be anything. Let us say it is V1, V2 and V3. It could be any value. I'm just giving you some values, 1.1, 0.6. Okay. What do we find? That the total potential difference across all three of them. So did you see the diagram which is given? How have they connected? Across all the three of them. So all these three are going to be taken away and we are going to put only one across and measure the total potential difference between these 3 points. Okay. So that will be nothing but a summation of all the 3 of them. You can actually do it in the lab and see how it has to be done. Is that okay? So we get total V is equal to V1 plus V2 plus V3. So it is a summation of the total voltage. Is that okay? Yeah. Okay. Let's see how do we actually substitute Ohm's law. So now what did we get? V is equal to what? You are talking about V1 plus V2 plus V3. Here, page number 183, activity 11.5. See that? Activity 11.5. Yeah. Did you see this? Did you see this diagram? Okay, so that is what they have done. So we get it as V1 and V2 and V3. Now according to Ohm's law, what does it say? V is equal to IR. Okay, now I'm going to substitute for each one of them. Pay attention. V is equal to IR. V1 is I R1 plus I R2 and I R3. Why did I put only I here? Because it is the same I. I is the current, so it is the same current which is passing. So I is going to be a constant. Okay. So this is, I'm going to find out what is the total resistance. So I is constant. So therefore, we get R S is equal to it is nothing but the summation of the individual resistors. You understand? Yeah. Now the diagram has been repeated twice. There's one on page number 183 and there's also one on page number 181. It is the same diagram. Except here they have not shown the individual voltages, okay, voltmeter, but here they have shown them each voltmeter, right? You perform each of these steps and then you finally come to this step. Okay, so they have shown you in 2 different diagrams. So for both the diagrams, you just write on the top RS. This is with RS. This is also RS. What is RS? Resistor in series. Is that okay? Come on, write down. First, we read a couple of sentences underlined. Okay. Read.
Resistance of a substance of resistance. And we learned about resistance of electrical electrics. We have noticed how the current through a conductor depends upon its resistance and the potential difference across its end. In various electrical gadgets, we often use resistors in various combinations. We now therefore intend to see how Ohm's law can be applied to combination of resistors. There are 2 methods of joining the resistors together. Figure 11.6 shows an electric circuit in which 3 resistors having resistance R1, R2 and R3 respectively are joined end to end.
Underline this. They are joined end to end. What does it mean? Okay, like this. If I have to just show you with the help of like this, end to end. Got it? So that is how the resistors are connected. Okay.
Here the resistors are said to be connected in series. Figure 11.7 shows the combination of resistors in which three resistors are connected together between points X and Y. Here the resistors are said to be connected in parallel.
So which diagram is this now? That is parallel diagram, not this. Okay, that is RP. How do we write RP? Resistors in parallel. But now, right now, we are not doing RP. What we have done is resistance in series. Okay. Somebody from this session, shall I continue?
Resistance in series. What happens to the value of current when a number of resistors are connected in series in a circuit? What would be their equivalent resistance? Let us try to understand these with the help
What is the meaning of the word equivalent? Underline that word, equivalent resistance. That means total resistance or final resistance. That is your equivalent resistance. Activity, no, I think that's I've already explained.
You will observe that the value of the current in the ammeter is the same, independent of its position in the electric current circuit. It means that in a series combination of resistors, the current is the same in every part of the circuit or the same current through each resistor.
Okay, underline that. The current is the same in every part of the circuit. Arush, did you underline? What is same? What is same here? Current is the same. Yes, very good. Okay. Go to the next page. Activity I've already explained to you. Okay. Arush, read the next one. You will observe. Next
You
page.
will observe that the value of the current in the ammeter is the same, independent of its position.
That's over.
Next page.
You will observe that the potential difference V is equal to the sum of the potential difference V1, V2 and V3. That is the total potential difference across a combination of resistors in series is equal to the sum of potential difference across the individual
Underline
resistors.
that sentence. There are a lot of words. Is equal to the sum of potential difference across each individual resistor. So you have to be careful when you are writing your paper. If you miss out one or two words here and there, it does not make any sense. Is that okay? In the electric circuit.
In the electric circuit shown in figure 11.8, let L be the current through the circuit. The current through each resistor is also L. It is possible to
Current is what? I. So is the current changing? Is the current changing? No, it is the same current which is flowing to all the resistors.
It is possible to replace the three resistors joined in series by equivalent single resistor of resistance R such that the potential difference V across it and the current I through the circuit remains the same. Applying the Ohm's law to the entire circuit, we have V equals to I.
What is V? I? R? Resistance. Pay attention because 2 minutes later I'm going to ask you questions. Continue.
On applying Ohm's law to the three resistors separately, we further have V1 equals to 1 into R1, V2 equals to 1 into R2, V3 equals to 1 into R3. From equation 11.11, 1 IR equals to IR1 plus IR2 plus IR2. R
Yes.
RS equals to R1 plus R2 plus R3. We conclude that when several resistors are joined in series, the resistance of the combination RS equals the sum of their individual resistance R1, R2, R3.
Underline that. That's your final statement. Where total R, that is the equivalent resistor, is nothing but the sum of the individual resistors. Now in your notebook, come on, write up. Quick, resistors in series. First point. In a series combination, of resistors, the current is the same through each resistor. Okay. Next point you will write. The three resistors. It may be three, it may be two, whatever. Okay. If the resistors are joined end to end, then the resistors are said to be connected in series. Okay, very good. Next point. The total potential difference across the combination of resistors is equal to the sum of the potential difference across each resistor. Across each resistor. Okay. Now from here you write. Therefore, this point. Therefore, V is equal to V1 plus V2 plus V3. Can you voice?
Yes, sir.
Okay. I'll write one little bit once a second. Applying Ohm's law. Next line. Next line. Substituting the values. And this is your final expression for resistors in series. Final statement right now. Therefore, this is S. Therefore, the resistance of the combination that is RS is equal to the sum of individual resistance
That is equal to.
it is equal to the sum of individual resistance, and it is greater than the greatest resistance. Also write down, and it is greater than any individual resistance. Is that okay? I'm just giving you a simple example here. Suppose I want to find out RS. Okay. And I'm giving you R. You already know that it's equal to R1, R2, and R3. I'm just giving you some values so that you understand it, okay? Let's say 1 is 24. What will be the unit? Oh, R1 is, let's say, 1 and this will be 20. How much is that now? Correct? So your RS is 45. See the last statement that I made. Okay, this is an example. So therefore, your equivalent resistance is equal to the sum of the individual resistors, and it is greater than the greatest one. Which is the greatest of all these? 24. It is greater than the greater resistor. Okay, so when do we use RS? When we want to increase the resistance of the series. That is how we always connect the unit. Is that okay? Did you understand? Write down one more point. Therefore, RS is used, that is, resistance in series is used to increase the resistance of the series. To increase the resistance in the circuit. Increase the resistance in the circuit. Okay, I'm just giving you some numbers here, only for you to understand. Okay. Now you remember we wrote a table there. Go back to the table. There's one more thing that we have to write. See the table. V, I, R, all that we have written. क्या लिखा था last time? R लिखा ना? R was the last row. Okay. Now if you have not written, write down row. So row is something that we have not yet added. Yeah, I will make it a river. Correct. Rho is resistivity. And what is the SI unit? Ohm meter. Okay. Next is I will give you a list of formulas later on once we finish. But it's very simple. Most of it we already know. What do we have next? Chemistry. Okay, thank you, class. Stretch your legs. Stretch your legs. And who is not whose book is that? Back. Where's your book? Okay, then you don't, you will find it. What happens to your book? Okay, then you forget yourself once. Please, because you are the ones who are using it. Take it again. Very cute.